And then after you kind of go through this overall assessment, looking at these key functions and instrumenting them, if you want to get down to the sort of the nitty-gritty detail of what's going on there. And then for performance in serial, then you want to look at using hardware counters to assess how it's running in serial on the hardware. And then in parallel, you'll be looking at regions of the code that are still serial and haven't been parallelized sufficiently, which again, the definition of that will change as you scale up orders of magnitude, and also identifying load balancing issues in the code. And then to address these, the problems in serial, you'll identify the regions of the source code that are not running efficiently in serial, and then you'll try to determine what the cause of that is, and then correct it. And in parallel, you'll be looking at where the communication bottlenecks are. You might be able to use something like tracing there to identify cause and effect. I sort of hinted at this at the beginning too, but these things really do go together. And although we'll be focusing on looking at eliminating the parallel bottlenecks, we'll be showing how to use the tools to identify some of these serial issues also. We won't be going into all the details of optimizing code in serial, but it's important to say at the outset, just as you need to design your code to be parallel from the outset, you also, before you start analyzing the performance of your code, really in parallel, you should make sure that it's running efficiently in serial. It's really easy to make a very scalable code that runs terrible in serial because the computation is so high that it covers and masks all the communication. But there's not much point in that. So it's important to make sure that at least your code has reasonable performance in serial before you really try optimizing in parallel, so that you're not optimizing in parallel only to find out that you really just need to make the code more efficient in serial, and then all the parallel bottlenecks will be different because the balance of work, computation, and communication will be different. So we'll start off at assessing the overall performance. Is there a performance problem? Maybe is probably the first question to ask. And how do you decide whether there's a performance problem? Different types of codes take a long time to do. For example, a quantum calculation may have only a few atoms, but it could take weeks to finish. So obviously it depends on exactly what's being done. And where are the problem? Is there, first and foremost, is there a significant problem when you run it in serial and running on the hardware efficiently in serial? And then you can start assessing how it's doing in parallel. So for serial performance, just sort of a very rough estimate of getting an idea of how your code is running in serial is to look at the fraction of the theoretical peak floating point performance that your code is getting when it runs in serial. So now this is very, very rough rule of thumb, and it very, very much depends on the algorithm you're running and exactly what you're doing. But in general, for a full scientific application as a whole, if that application as a whole gets 20% of the theoretical floating point performance of a machine, then usually that's decent. That's in the ballpark of being a decent efficiency. Now, if you're just doing a matrix multiplication, then there's fast libraries like dgem that can do that at like 90% of the theoretical peak. And so if it's that's getting 20%, then it's awful. So again, you have to take that with a grain of salt. But if you're looking at the full application as a whole, and you're using fast libraries, as I think you heard about this morning, if you're using fast libraries for those things that have those things available, and that for those things that are highly optimized, that can run at very high percentage of peak, if you're doing those sort of things, your code is getting this kind of performance, then it's probably in the ballpark. But again, you should assess that and look at the algorithm and see what should you expect to get from that algorithm. Well, this is kind of a rule of thumb. If a code gets 40% of the peak performance, and it's just for a general scientific application, that's usually really, really good. So it's easy to calculate that if you can determine how many floating point operations you're doing per cycle. So each architecture, each processor architecture will have a certain theoretical number that it can do 2 floating point operations per cycle or 4 floating point operations per cycle. So you can go down and measure this with these performance tools. You can see how many floating point operations were done, how many cycles passed, and you can get the number of floating point operations per cycle. And if you want to get the flops, the floating point operations per second, then you just multiply that floating point operations per cycle times the number of cycles per second, which is the speed of your processor, the number of gigahertz or megahertz that it runs at. Getting overall, we'll touch on that. And then I just want to bring out sort of this general rule, which seems to apply in lots of situations, is that generally you get 80% of the benefit after you do 20% of the work. So a lot of times you can find the glaring problems without too much effort and fix them, and that will get you 80% of the way there. And so that's something to keep in mind with all these things we'll talk about today. Is do you need to squeeze out that extra 20% of performance? If so, that's going to take some time and effort, but it could be worth it depending on what you need to do. So, and then with parallel performance, it's very simple, right? It's how well does your code scale? You can talk about strong scalability, which is you hold the problem size the same and then you just run it on more and more processors, and you should see the time decrease by in direct, if it's perfectly scalable, in direct relation to the number of processors that you run on. But there's also an issue of weak scalability, which is also can be important to look at, and that is if you double the number of processors and double the size of your problem, does the runtime remain exactly the same? And so those are 2 different ways of measuring the scalability, and there's different issues surrounding those, and it depends on what kind of work you need to do. If you need to make your problem run bigger and bigger problems, then the weak scalability is important. If you just need to run a single problem size, but you need to make it go as fast as possible, then you want to focus on strong scaling. Okay, so now we talked about detecting the overall performance, both in serial and parallel. And so now we're going to pull out our first, second tool. We're talking about PAPI, which is IPM. And so this is a very good tool to get overall picture of how your code is performing. That's what it's designed primarily to do. You can get the overall floating point operations per second of your code. You can look at the ratio of the communication and computation at different levels of parallelism. It's very quick and easy to use. It introduces almost no overhead. But then, of course, the trade-off is that if you want to get at the nitty-gritty details, then it takes a lot more effort. And I believe, someone correct me if I'm wrong, if this has been added, I didn't check before I wrote this, but last time I checked, it doesn't support OpenMP. So that's just something to know. This is an example of how IPM works, just to show how easy it can be on Ranger. There's a module for IPM, and you load it, and then you just run your program, basically. But before you issue the IB run command on, or MPI run command on some other machine, but it's IB run on Ranger, then you just set this environment variable. And then you run your code as normal. So it doesn't get much easier than that. You load a module, set an environment variable, and then just run. And then at the end, there will be you'll be left with a directory. You'll be left with some files that IPM creates, and so you want to load that command, and then you do IPM parse, and you can create an HTML file which has a summary of the performance of your code. So so you don't need access to the source code, as I mentioned before. You can look at this overall performance just with your binary. You don't have to recompile. You don't have to do any of that. So this is an example of with unres without IPM. The MD loop took 51 seconds, and with IPM it took the same. So it's just there's no overhead involved in that. Was there any question at this point? I thought I heard something over the speaker, but just wanted to check. Yeah, it took slightly less. I mean, that now you're just machine noise. And whenever you do these measurements, you always want to check for machine noise. Some machines, when they get really heavily loaded or whatever reason, there's sometimes significant variability between the runs. And that could be really a pain when you're trying to get scientific results. You may have to get error bars on that depending on if you start to see a lot of variability. So you should run, whenever you do these things, you should run multiple times if you really want to be sure that you're seeing a real effect and not just the effect of lots of traffic on the network or something like that.
Minnesota has a question.
Okay.
I just want to know the IPM, I believe it's a public domain software, right?
Yes. Yeah. Well, it's no. I guess I don't know that. Public domain. I'm not sure. Actually, I have to check. My inclination would be that it's like an open source type project, but I guess I have to check.
So basically, yeah, I think it definitely is worthwhile to give it a try.
Yeah, oh yeah, it's freely available. I do know that much. I mean, it's certainly, you can download it, and anyone can download it and use it as much as you want. I think you could, I think it's open source, but it's certainly free to use. And it's been created through grants, from the government, and so it's the idea is that it's there, and it's installed on many of the systems on the TeraGrid. I don't have a comprehensive list with me, but I think we have a list of the ones somewhere that in this workshop that are available. I know it's on Ranger, but yeah, it's certainly, if you want to get a quick look at what your code is doing, then it's a really great tool to use.
So basically, for install it on a particular machine, you just need a specific version of PAPI, and so on top of that one, you can install the IPM, right? That's correct.
I don't think you need PAPI to run IPM. I think IPM can make use of PAPI if you have it installed. I may have to double check that. I'm pretty sure you can run it without.
Standalone.
But let me double check on that. But yeah, okay. So if you have PAPI, then you can get at certainly you can get at more information. I'm not sure if it uses PAPI to do to get all the cycles and so forth. I know it can. I'm not sure if it has to use PAPI, I guess is what I'm saying. But yeah, if you install PAPI and you install IPM on your system, then you'd be ready to go.
Hi, I have a question from Penn State.
Okay.
What is the finest interval you can go to in the sampling interval?
What's the finest interval that you can go to?
Yeah.
Well, so that's a good question. I'm not sure. I'm not sure. I haven't seen in a tool a place to control that, and so I'm not sure exactly how that's defined. I've never seen a tweakable parameter on any of these things that says you want to change the sampling, but that doesn't mean it's not there. So that would be another good question to look at. I wouldn't imagine that it's every. So I think that's part of where you get at some of the uncertainty, because it's not every clock cycle, and so because it would take forever, right? So I'm not sure what the finest is, but probably the answer is that you'd want to keep the overhead I mean, you want to be able to run your application in the same amount of time, and so that may be the limiting factor.